Hi everyone, so second installment of integration. This is the C2 element then. We're talking about areas beneath curves. So I've got a lot to do here. And we've already set up the background for integration. So for starters, we know that if y equals ax to the n, then if we integrate both sides with respect to x, then we go plus 1 to the power, divide by new power, plus c, remember. So this is our C1 element, that plus c, because we didn't know what the original curve was, if this was dy by dx, remember. So if we started with a gradient, we integrate both sides of that gradient, we end up with the dx in quotation marks cancel. We're left with integrating 1 then, and then 1 with respect to y goes to y, and then our integration plus c, right? And we need to know what that c was to find the particular solution. C2, however, depends on that second idea of what integration does. So remember, integration can find original curves or particular solutions, but it can also, among other things, find areas beneath curves. Now, we talked in class about the proofs behind this, so we're not going to do the proofs again, but I'm going to make it clear what's happening for integration. Integration, if you have a curve like this, right? So this is y equals f of x. If you integrate, so the area is the integral of f of x dx, which we talked about, but we need limits in there, okay? So let's say this limit was beta. Beta, the rightmost limit, goes on the top. Why? How's this working? Well, if I say I want to find this shaded region here, basically. I want to find this. So I'm going between beta and alpha. So my notation would be top limit, bottom limit, like that. What is integration actually doing though? We agreed in class that integration splits the area up into an infinite number of rectangles with zero width, i.e., as you told me in class, lines. And that goes from minus infinity all the way up to that boundary beta. How does this work then? What's this mean? This means add up all the area up to b, up to beta, okay, from minus infinity to beta, and then our lower limit alpha means subtract all of the area up to alpha. So if I subtract everything up to alpha, again the infinite number of lines up to alpha, then you're left with the area that you want, okay? So the theory says that once this is integrated, so notice lowercase means I haven't integrated yet. Once I integrate it, this will go to f of beta, capital F, means it has been integrated, right? Minus capital F of alpha. This is your C2 integration formula. So, what do I mean by that? How does this work? What I'm saying is, if I integrated, let's have an example. Let's say I've integrated y equals x squared plus 4. So this is 4 here, isn't it? And I want to know the area between 1 and 3, this shaded region here. So my area is the integral of x squared plus 4 dx. And remember, dx means moving along the x-axis from left to right between 3, my top limit, and 1, my bottom limit. So what I'm going to do is I'm going to go to square brackets, okay? So the integral sign, once I've integrated it, disappears, doesn't it? X squared goes to x cubed, divide by new power. 4 goes to 4x, so any constant, just x. Notice I've got square brackets with 3, 1 in there. So this is my capital F of x. So now all I'm doing is putting in my limits. So a third of 3 cubed plus 4 of 3. Do you see? Minus, and now x is just replaced with 1 plus 4 lots of 1. And if I put that in my calculator, I'm going to get so a third times 3 cubed plus 4 times 3, so that gives me 21 minus, and then a third plus 4 lots of 1 minus 13 over 3, so 21 minus your answer is 50 over 3. Now, I've done that, right? How do I know if I'm correct? This is where your silver calculators come in. So this is where we need to start using our calculators and checking whether we're right. So we're going to have an aim. So from now on, before we start a problem, we're going to go aim. So in our calculators, you find that magic button, the one that we used before to check differentiation but without pressing the shift, and you should get something that looks like that. So you're going to whack in the integral of between 3 and 1 alpha x squared plus 4. Press equals, and your aim is 50 over 3. Does it match? Yes. So we're happy, we know we've got it right. Okay? That's basic C2 integration. But what we're going to start doing, and what the more complicated problems occur, or when they occur, is when we're finding areas under curves. Okay? So scenarios. How does it work? Here's a basic scenario here. Let's find, so all the questions are prefaced with find the shaded area. Find the amount of area, okay? Now let's be really clear, like we were before, when we started talking about M1 displacement and all this kind of stuff. Remember, the integral of velocity is displacement, because displacement differentiated gives you velocity. Rate of displacement over change of time is velocity, isn't it? Okay? We want to find the shaded area. Not, like, as in we want to find the area, right? We don't want to find the integral between 0 and 7, because, remember, we want positive area. At the moment, this is positive area. But this bit is what's called, negative area, because if this was displacement, it means that it's moving in the opposite direction. Okay, so it isn't a negative area, of course. That means we've created a wormhole, but it's important to understand what's going on, and I want to prove this bit to you. Okay, let's prove it. So we'll have more practice with our integration. First off, what do we need? We need to know that coordinate there. Where does that cross the x-axis? Well, we need to go back to our equation, don't we? So if I factorize this, I get minus x plus 5. Therefore, this crosses when this thing equals 0, x is 0, which we already know, and x equals 5, which must be that point there. So x is 5, you see? So let's do this. First off, I'm going to find the area of that. So let's go for it. The integral, or the area of 1, should we call that area 1 and area 2? Is that easier? Okay, so area 1 is the integral between 5 and 0 of our y, so minus x squared plus 5x dx. Square brackets means I have integrated it. So plus 1 to the power, divide by new power. Plus 1 to the power, divide by new power. Now we're doing our f of beta, f of alpha. So we whack in our limits and actually show that you're putting those limits in. Minus, always minus the second lot. So third, 0 cubed plus 5 over 2, 0 squared. Whack that in the calculator. So minus a third times 5 cubed plus 5 by 2 times 5 squared. 125 over 6 and minus 0. So 125 over 6 is area 1, yeah? Which you could quickly check in your calculator. Let's do that. So put in 5, 0, magic integral button, minus alpha squared plus 5 alpha x. And we do get 125 over 6, so we're happy. Let's do area 2. So area 2 is between 7 and 5, isn't it? Right? Remember, biggest one, take smallest one. So 7 and 5. Same curve, and let's see what happens. So if we do that again, we integrate it, square brackets, always square brackets, plus 1 to the power, divide by new power, you'll see it's exactly the same as the other one. Whack in your limits, so 7 cubed, 5 over 2, 7 squared, minus, and now minus a third, 5 cubed, plus 5 over 2, 5 squared. And we end up with, so minus 1 over 3. You're good if you're doing this too, just to check. 7 cubed plus 5 over 2 times 49. So that's 49 over 6 minus 1/3 times 5 cubed plus 5 over 2 times 25. 125 over 6, which equals, so 49 minus 125 over 6 is minus 38 over 3. How can we have a negative area? So I'm saying that the second area is negative. It makes no sense, does it? It doesn't make sense because our integration puts it in the context of displacement, velocity, acceleration, or whatever. We are trying to find the area of the shaded region. Okay? So, scenario 1, we need to split areas up. Split areas up. Because if below x-axis, right? If you understand what's going on, you're going to get a negative area. You need this to be positive. So area 2 is going to be the modulus. Can you see? The modulus means the absolute value, doesn't it? Of that answer. So it's just 38 over 3. But only if you understand what's happening. In other words, if you do the modulus of this thing, the absolute value, the maths treats your area as it being up here, okay? And therefore you can add the two together. So therefore total area is 38 over 3 plus 125 over 6. So 38 over 3 plus 125 divided by 6. So 67 over 2, okay? Let's try again. So that was scenario 1. So scenario 1, if you had any kind of problem where it was like that, for example, a need to find shaded region, you would need to split this up into 3 different sections. Area 1, Area 2, Area 3, and Area 2, you would have to mod the whole thing to show that you are considering that it's positive area. Okay? Scenario 2. This time, we've got coordinate axes here, right? We've got our curve, y equals x squared minus 4x, and we've got a line, y equals minus 4. And the area it wants is the area between the curve and the line y equals minus 4 as shown. This looks difficult, doesn't it? But actually, it's fine. There are a couple of ways that you can do this, okay? The most obvious way is to find this area. Can you see? And can you see that this is a box? So if we can find the area of the box and the area of this shaded region and take it away, perfect. But remember, hopefully you're saying it, this red shaded area, this is going to be negative. So we need to take the positive of it, the modulus of it. Let's do it then. First we need to know, like always, where this thing crosses the x-axis. So this crosses the x-axis when this is 0, x is 0 and x is 4. So this is 4 and this is 0. Therefore, the area 1, the red area, is the modulus, isn't it? Because it's going to be negative. Between 4 and 0 of x squared take 4x dx. Modulus, square brackets, 4, 0. I have integrated it, so a third, plus 1 to the power divided by a new power, plus 1 to the power divided by a new power, and that leaves me, whoops, that should be a mod, and that leaves me with the modulus of 4 going into these limits. So 4 cubed minus 4 over 2, 4 squared, minus, and now whack in your 0, 4020 squared, and all modded. And this will equal, if you whack that in your calculator, so a third of 4 cubed minus 2 times 16, whoops, minus 2 times 16 is minus 32 over 3, but it's all modded. So the area is 32 over 3. That's that red area there. What's the area of the box? So area 2, well, we know this is 4 across, and, well, y equals minus 4, so this is 4 going up. So the area of the box is 16, therefore total has to be area 2 subtract area 1. So 16 subtract 32 over 3 is the same as 16 minus 32 over 3, 16 over 3. And there we go. There's our shaded area. Okay. We will need another video anyway for the trapezium rule. So we'll leave it on this scenario 3. Scenario 3. This looks horrible, doesn't it? We've got two curves. So by the way, scenario 2 could be called the method of subtraction. So I used a shape, a standard shape, and then I subtracted the area from it. Okay? Scenario 3, this time, can you see I've got two curves intersecting at this point and this point? I need to find the shaded region encapsulated between the two of them. Right. How does the theory work behind this? So, this scenario is areas between curves. Now, if you have areas between curves, it's always the same method, and hopefully you're going to understand why. So my method is always top curve, area, subtract bottom curve. So pay attention really closely to this, because you can make life a lot easier for yourself if you follow this idea. Now, can you see this top curve is this one, right? How does integration work? Well, first we need to know these limits, because it's going to give us all of that area here, isn't it, between the x-axis and the curve. Likewise, if we integrate the bottom curve, the red one, between these two limits, it's going to subtract all of this, and then we're left with the area that we want. Do you see? Let's kill two birds with one stone then to find the intersection. We need to know these x coordinates to get this done. So, top curve minus bottom curve. Top curve, when does the top curve equal the bottom curve? I'm always going to move my bottom curve, so it's top curve minus bottom curve. You'll see why, because it just makes the integration really easy, right? So minus x squared, so that's minus 2x squared, that's moved over there. plus 4x minus 4x minus 4x, sorry, so that's plus 8x. And minus 1 minus 5 is minus 6 equals 0. Keep hold of this. It's very tempting now to divide by 2, isn't it? Simplify up your algebra and maybe times it all by minus 1. So now you can see how you can factorize that. No, I'm doing that quickly. 3, 1, so it's got to be minus and minus. So you guys can do all that, that's no problem. So this is x equals 1 and x equals 3. Okay, so to show you why I'm saying pay special attention to how I've laid this out, if we were to find that shaded area then, that shaded area would be between 3 and 1, top curve, which is this one, minus x squared plus 4x take 1, minus the bottom curve, which is this one, between 3 and 1, x squared minus 4x plus 5 dx. Do you see? But I can save time by, instead of working that separately, that one separately, I could put them together. They're both in the same limits. Do you see? So 3, 1, and you see if I put them together, it's exactly what I did up here. You're just going to end up with minus 2x squared plus 8x take 6. The danger is that you put this one in, but because that's not the curve, is it? This is the curve that describes the intersection. And now we integrate as normal. Square brackets, plus 1 to the power, divide by new power. Plus 1 to the power, divide by new power. Plus 1 to the power, divide by new power. Put in your limits. Q plus 8 over 2, 3 squared, 6, 3, minus, now with 1, 3, 1, etc. And you'll get your answer. We're running out of time now, but I just want you to quickly, so if you finish that off, whack in your aim using your calculator, remember your aim. So I'm saying between 3 and 1. If I just quickly put this in my calculator, I've got minus 2 alpha squared plus 8 alpha minus 6. The answer should be 8 over 3. So you guys check that. Make sure you're using the calculator. You see how useful they are. Really useful. Next video.